In Chapter 9, we get to discuss hypothesis tests, and these are tests about the population mean and the population proportion that we're going to do. And this is really the culmination of everything that we have been studying together this semester. The first thing we need to do is get familiar with some of the terminology. In hypothesis testing, you have two opposing views or two opposite views. One is the null hypothesis. We call that one hypothesis 0. The null hypothesis is a claim about a population parameter that is assumed to be true until we can declare it false, until, in other words, we reject it. Your other hypothesis is the alternative hypothesis. Now we call that hypothesis 1. That's a claim about a population parameter that will be declared true only if the null hypothesis is declared to be false. In other words, we don't really make a decision about the alternative hypothesis. Our decision is about the null. We either reject it or we fail to reject the null. Now, a note, when you're setting up hypothesis statements, we usually set up the alternative hypothesis first. The alternative hypothesis is the idea of the researcher. It's the thought that caused him to do the research. What if salaries are different than they used to be 10 years ago? I want to see if that's true. What if the price of eggs has actually gone down since 2018? I want to check and see if that's true. So this is the idea of the researcher, and that always goes into the alternative hypothesis. The null hypothesis will then be set up. It will be the opposite of the alternative hypothesis. So we have the two opposing views. Now, the null hypothesis will always include an equal sign of some kind. It may be an inequality, less than or equal, greater than or equal, but it will always have equal in some form or fashion in the null hypothesis. The alternative hypothesis, however, never includes any type of equality. It will always be some inequality sign, less than, greater than, or it might be a not equal to sign. So let's take a look at the decisions that can be made based on this null and alternative hypotheses setup. First, the question is always, should the null hypothesis be rejected or not? That's the only question we're going to answer with our research. Now, a hypothesis test only tests the null. Keep that in mind. If the null hypothesis is found to likely be false, then we would say that the alternative hypothesis is adopted, but we usually say that the alternative hypothesis has merit. Nothing can be proven on the basis of one experiment. The alternative hypothesis, however, once again, is never tested. We only test the null. Now, since the result of any hypothesis test is not guaranteed to be correct, there are four possible outcomes. Two of these possible decisions are incorrect. And you need to be familiar with these. Now, I've put it in a little chart here that I would draw myself, learn. I would go over it until you understood this one, okay? And it tells you the actual situation, and it says the decision that was made. Now, there are four possible outcomes. One is the decision to not reject the null hypothesis when the null hypothesis is true. Now, so what if the null hypothesis is true, and we make the decision to not reject the null hypothesis, okay? So the null is true, and we made a decision, do not reject it. Well, that was an okay decision. And then another decision would be, what if the null hypothesis is false, and we made the decision to reject it? That's also a correct decision, so that's okay. But then two errors might happen to us. For example, the null hypothesis might be true, and our research didn't show that, and we made a mistake and we rejected it. So based on our research, maybe our research was in error, maybe we didn't have a true representation of the population, whatever the reason, we rejected a true null hypothesis. We call that a type 1 error. The type 2 error is we have a false null hypothesis and we don't reject it. So we accept or we don't reject a false null hypothesis. Now that one's called a type 2 error. Now I want to look at this on the bottom of page 1 with another example that might help you to understand a little better. And the example I'm going to use is a court trial. In the United States, when we go to trial, when we take a defendant to trial, they are considered innocent until proven guilty. Thus, innocence, we would say, could be thought of as the null hypothesis, right? So we would say not guilty is the assumption. The null hypothesis when we go into an experiment is the assumption. So we're going to say not guilty right here is what we assume to be true. And then, of course, the other situation would be that they are guilty. And then the court's decision has to be made, okay? The court's decision, we would say, okay, they can do a not guilty or a guilty. So that's the way it happens. Now, what happens if we have somebody who comes in who is actually innocent and the court finds them innocent? Well, that's correct decision, right? They're innocent, the court found them innocent, everything's great. What if we have someone who comes in to trial who is guilty and the court finds them guilty? Also another correct decision. And then there are the other two scenarios. We have a not guilty person who is found guilty. Now that is what we call a type 1 error. Now I consider a type 1 error to be the worst type of error, and in research it is considered to be worse than the type 2 error. A not guilty person is found guilty. You can associate this with the court's decision. This is an innocent person going to jail. That would be, to me, the worst scenario. What's the other scenario? Guilty person goes free. That's our second type of error. It's the type 2 error, and in my mind, I would rather see a guilty person go free than an innocent person go to jail, and that's how I keep track of which one is type 1 and which one is type 2, and perhaps that will help you. Now, I want to go back to the 3 scenarios for confidence intervals that we've talked about before. Remember this? We said a confidence interval for the mean or the proportion. We either, if we're checking on the proportion, well, we always use the z-table. If we were checking on the mean, we need to know if the population standard deviation is known. If it is, we use the z-table. If it's not, we use the t-table. That's what we did for confidence intervals in Chapter 8. Just remember, we're going to do the same thing for hypothesis testing, so that's not going to change on us. We do, however, have different types of hypothesis tests. So where confidence intervals, we're always basically splitting alpha into 2 parts and putting 1 in each tail. That would be considered in hypothesis testing a 2-tailed test. In a 2-tailed test, there's a rejection region in each tail, in both tails of the distribution curve, just like we did in confidence intervals. Divide alpha by 2, put half of it in each tail. And then we have 2 other types of tests for hypothesis testing. We have the left-tailed test, where the rejection region is all in the left tail of the curve. No longer do we divide alpha by 2. Or a right-tailed test, where the rejection region is in the right tail of the curve. Once again, no longer do we divide alpha by 2. So how do we figure this out? Well, first, we look at the sign in the alternative hypothesis. If the alternative hypothesis has a not equal sign, then it's a 2-tailed test, because it could be rejected if it's too high or if it's too low, if it's in the positive side or the negative side. So we have to have those 2 rejection regions. That's our not equal. If the alternative hypothesis has a less than sign, it's a 1-tailed test, and the test is all in the left tail. Note the arrow in your hypothesis is really pointing you to the rejection region, isn't it? If you think about the inequality sign as an arrow. On the other hand, if the alternative hypothesis has a greater than sign, well, we have a 1-tailed test, and all of the rejection region goes in the right tail. So let's look at an example. Now this is according to the U.S. Bureau of Labor Statistics, and it says that workers in the U.S. who were employed earned an average of $56,516 a year in 2015. So we are an economist, we're a researcher. We want to check and see if this average or this mean has changed since 2015. Now note, the words I used, the question I ask as a researcher is, has the average salary changed? Has changed is key to us. Has changed means it could have gone up or it could have gone down. It could be higher or it could be lower than it used to be, and it would still answer my question, yes, it has changed, right? So in that case, we set up our alternative hypothesis, and remember, that's the one we always set up first, and we say the mean, and the test is always about either the mean or the proportion, population mean or population proportion. We say the mean is no longer equal to what it used to be. That's the old average, isn't it? So we say the mean is not equal to what it used to be, and that means it has changed. And the alternative then the null we set up says the opposite. It says it has not changed. That would be it is equal to what it used to be. Now, when you're drawing the curve, and this is going to be really important to you, like I said, you're going to take your alpha, your confidence level that you're interested in, and you're going to split it into two pieces. And you're going to put, for a two-tailed test, you're going to put one in each side, just like we did for confidence intervals. And then we're going to center it around our population, our old population mean, and we're going to say, if we do a test and I take a sample, and that sample comes out either high enough or higher than 56,516, and it falls into this rejection region, I will reject the null, or if it is much lower than. Now, please note there's an area in between here that still would be higher than the mean, old mean, or lower than, but it's not high enough, is it, to cause us to reject it? And that's an important thing to note. When you are doing a hypothesis test, if it's close to the mean, in either case, well, it hasn't changed enough. And we call that a significant difference. When it is far enough higher than the mean or far enough lower, it's considered a significant difference, and that's when it actually will fall into these rejection areas, okay? In other words, if I was looking at a salary of $56,516 a year in 2015, and the current salary was $57,516, well, it changed. It had changed by $1,000, right? But that's not enough. That is not enough for me to reject the null. Now, let's look at another example. This one is an example of a left-tailed test. So it's we're talking about this time the mean amount of a soda in soft drink cans produced by a company. And the company claims that these cans, have 12 ounces of soda in them. That's their average. They're saying, they contain 12 ounces. However, if they contained less than that amount claimed, then the company is cheating people, right? So there's a consumer agency, and they want to test whether the mean amount of soda per can is less than the 12 ounces. Now, please note, this is a consumer agency. They always, if you see a problem that is talking about the consumer agency is checking a company, they're always checking to see if the company is lying. So they wouldn't really care if the company was actually putting a little more than 12 ounces in. That wouldn't concern them at all. What are they interested in? If the company's cheating people, if they're selling 12 ounces of soda and they're really putting less than. So that's our test. The agency says, and they set up this research, we believe that they are selling soda and it's less than 12 ounces in a can. That is my alternative hypothesis, right? I'm the researcher. I am the consumer agency. I say, I believe the mean is less than 12. In other words, they're cheating people. What's the null hypothesis then? Well, the mean is equal to 12, or it could be greater. Either way, right? Now, sometimes in programs you'll see, or in problems you may see just equal here, but I like to put all of the rest of the alternative in here. So I like to put greater than or equal, because that would also be part of the null hypothesis, because they don't care if it's greater than 12. So that's the way I usually list it. Now, let's go down here and set up our rejection region on the curve. And we look again at the alternative hypothesis and we say, okay, rejection region is going to be over here in the left. It is all of alpha this time, because I only have one rejection region. So I set up this area over to the left, and of course my mean is dead set in the center, and that's my old mean, the one I used to have. And then I will do a test. I'll take a sample, I'll check a bunch of soda cans, and I'll measure them, and I'll see how much is actually in them, and I'll have a test statistic that I see whether it falls into the rejection region or not. So our third type of example that we want to look at is a right-tailed test. Now, according to this website, the average price of homes in West Orange, New Jersey was $471,257 in 2013. Now, there's a real estate researcher. He wants to check and see whether the current mean price of homes in New Jersey, in West Orange, is actually higher than $471,257. He's interested in knowing if the value of the houses has gone up. So this key phrase we got here is he wants to know if it's higher than. That means the alternative hypothesis says, I believe the mean is greater than it used to be. The mean is greater than it used to be. Now note, there's never an equal in the alternative, but there's always an equal in the null. So what's the null? It says, well, the mean is equal to what it used to be, or it could be less than. So it covers all of the other cases. I like to include that inequality in it because it could satisfy that null condition if the value of homes has gone down. This time we set up our rejection region in the right tail because, look, our alternative hypothesis points us to that right tail. We don't divide alpha in two. We put it all in that right tail. And, of course, the mean right here that we're comparing our test statistic against is going to be right here in the middle, and it is the old mean of homes that we had. What we're comparing to goes in the center as the mean. So just so you'll have a little chart that you can go back to on page 4 if you want to, this is a summary of what we do with the null and alternative hypothesis and the different tails of the test. A two-tailed test will always have a null hypothesis of 0, an alternative of equal, and an alternative of not equal. The rejection region in that case will be in both tails, and we will divide alpha by 2 to create that rejection region. If we have, however, a left-tailed test, well, our null hypothesis says greater than or equal, and our alternative points to that left tail, doesn't it, with the less than sign. Where do we put our rejection region? It goes in the left tail, and it is not divided. Alpha's not divided. All of alpha goes in that left tail. Now, the opposite, or the same, is true of the right-tailed test. The null hypothesis says less than or equal. The alternative points to that rejection region in the right tail, doesn't it? And the right tail contains all of alpha. Again, alpha is not divided by 2 for a one-tailed test. This left and right-tailed test are considered one-tailed test, and the two-tailed test, or the equal, not equal, is always considered a two-tailed test. Now, another summary of information here on page 5 that I've given you is the procedures for checking for rejecting or not rejecting the null hypothesis. One is the p-value method. Now, the p-value method is actually the most widespread one we use out in the real world, but we're going to use both because we're first learning. We're just learning about hypothesis testing. So we're going to use the p-value, and we're going to use another method. We're going to draw the curve and see where the test statistic falls. So it's important to learn and understand both methods for this course, and both of your methods will be included on your test and homework assignments. First, the hypothesis test steps for the critical value method. Now, this is where we actually find the test statistic and see if it falls into the rejection region. The first thing to do is state the null and alternative hypothesis, and you will always state the alternative, figure out the alternative first, and then the null is the opposite. And second, you're going to use the correct distribution for the test. If it is you're going to use either the z-table or the t-table, right? If it is a test of the proportion, or if you know the standard deviation of the population, you will choose the z-table. If it is a test of the mean, but you don't know the population standard deviation, you have to use the t-table, just like we did for confidence intervals. Third, you're going to draw the rejection region. You're going to draw the null model and put your rejection regions in there, and that's going to be based on the significance level of the test. In other words, that's going to be based on alpha. And then you will calculate the value of the test statistic. Somebody took a sample, and they came up with where that sample fell on your model that you've just drawn, and then you'll be able to make a decision. Now, there's a p-value method, which follows some of the same steps, but pay close attention to what we do differently with the p-value. We do state the null and alternative hypothesis the same way, and we select the correct distribution for the test. And then we calculate the value of the test statistic, and we calculate the p-value, and we use those two to make a decision. The test for p-value is always, is p-value less than alpha? Now, not alpha divided by 2, even in a two-tailed test, it's always got to be, is p-value less than alpha? If it is, then we know the decision is to reject the null. So let's look at some pretty familiar formulas because we've just finished with critical intervals, and let's look at some things that you're going to be using and how we'll be calculating z for the sample mean. And what we'll be doing first is we're going to use the normal distribution, of course, if we know the population standard deviation. And this normal distribution is always for populations that are normally distributed or sample size is 30 or more. That still holds true. Now, when we're calculating z for the test of the hypothesis, now this is our, this is actually the sample that we're going to pull, and we still have to figure out where it falls on the curve, on the test that we've drawn out. Then we do the same thing. We say, same thing we always done, we say the sample mean minus the population mean divided by that standard deviation that we adjust by dividing it by the square root of n. So this we call the observed value of z. They call it the test statistic quite often. This is the sample that we took, and what did we observe when we took that sample? We came up with a test statistic, and this is the one we're going to see where it falls on our curve that we've drawn to see if it falls into a rejection region or not. So let's look at a specific example, an exercise on page 6, and I'm going to go through it with you. There was according to NBC News, college students spend an average of $158 on course materials per course. However, there's a college affordability committee, and they suspect that that average cost of course materials has actually increased since 2018 when this was tested, or when this was determined. So they took a recent sample of 100 college courses, and they found that students spend an average of $167 on materials per course. Now we're going to assume that the distribution of all these course materials is normally distributed with a standard deviation of 40, and we're going to use a significance level of 5%, and we're going to ask the question, do the sample data provide enough evidence to support the claim that the average cost of course materials has increased since 2018? Now, with word problems like this, your first job is to read it, and then your second job is to read it again, finding the pieces of information that you need. So let's go back through it. It says college students spend an average, in 2018, college spend an average of $158. Now, I'm believing that that is the old mean, okay? Because that's what they used to spend, and that's where my comparison starts. They think, this college affordability committee suspects the course materials, what do they expect? Well, they expect they've increased. A recent random sample of 100, well, that's n, isn't it? Found that students spend an average of 167. Well, now that is a sample average or a sample mean, isn't it? So they spend 167 on course materials per course, and we're going to assume the distribution of all. Now look, all course materials is normally distributed, so the population is normally distributed. And we're still talking about all has a standard deviation of 40. There is my population standard deviation. So I have that. I can use the z-table. I'm going to use a significance level of 5. And it says, do the sample data provide enough evidence to support the claim that the average cost of course material has increased? That's my question. Has it increased? We're going to use the critical value. We're also going to use the p-value method to do this. Now let's pick the pieces that we found out. What is the old mean, the one we're comparing against? Well, that was $158. That's what it used to be. We took a sample of 100, and out of that sample we got a sample mean of $167. Looks like it's different to me, doesn't it to you? But we still don't know if it's different enough to reject the null hypothesis on this one. And then we're going to say the standard deviation. Do we know the population standard deviation? In this case, we said it was a population standard deviation. We were given $40, and we need alpha. Now, this is a little bit different from what you were looking at in confidence intervals. Instead of saying, 95% confident, they're giving you the other side. They're giving you actually alpha. They're saying a significance level of 5%. So there it is. My alpha is 0.05. And then I can do my standard deviation adjustment. But I want to come down here next, and I want to say, let's set up our hypothesis. This one first, right? Set the alternative first. And the alternative is, what are we looking for? We're looking to see if the average cost of course materials has increased. In other words, if that population mean has actually gotten bigger. If it's bigger than it used to be. Now, I want you to note something about these hypotheses. When you're dealing with the population mean, you're always going to start them with the mean. They're always going to end with the old mean, whatever it used to be, the thing we're comparing to see if it's different, okay? So this one is the same way. The only thing that changes here is the symbols in the middle. This one says greater than, the null has to say less than or equal. It is the opposite. It takes everything else into account. So then you ask yourself the question, which distribution do you use? Well, the question is really, do you know the population standard deviation? If yes, you use the z-table. Now I'm going to go back up here and do my standard deviation adjustment that I have to do. I'm going to take 40 and divide it by the square root of the sample size, which was 100. So really that's 40 divided by 10. I can do that without a calculator. It comes out to 4, okay? Now, and we're going to find next our rejection region. I'm going to move this up just a little so we can see everything on the page. And let's sort of draw this curve for us. I've given you some curves. The center is set up to be 0, and we're using the z-table, so we'll go ahead and say that's our z-table. And then underneath it, what are we looking at? Well, we're looking at a mean of 158, right? This is the sample mean of 158 because that's what we're actually looking at. And that's the old population mean. That's what always goes here. Now, I want my rejection region to be where? Well, look at the alternative. I got to put it in the left tail. So I'm going to come over here and say I got a rejection region. It's over here in this tail. And how big is it? It's my rejection region. It is 0.05. It is all of alpha because I don't divide alpha for a single tailed test. So I need to know what this z-score is, don't I? Don't I need to know the z-score there? So I'm going to say, okay, if it's 0.05 in that tail of the test, well, I can look it up on the negative side, and I know instead of being a negative z, it would be the same z. It would just be a positive z, right? So that's what I'm going to do. Now, remember me telling you that on this particular test, chapters 8 and 9, really you don't need the negative, you don't need the positive side of the z-table at all. You're really going to do everything with the negative side. We're going to come over here and say, where is 0.05? That area, where is it? Well, it's between these two numbers, and I always go, I know this one, and I always go with 1.65. You could have done 1.64, and you would have still been fine. But I'm going to say this is a 1.65. Is my z for that one, and so that kind of tells me. And the rejection region, of course, I've already set up. It's over here, okay? So now that's really set. If I do my test, I have my sample, and if it falls into this rejection region when I figure out my sample, then I will reject the null hypothesis. But let's see where it comes out. First, we have to come up with what we call, and we said critical z. Now this, I want you to note, critical z is 1.65. In other words, that is the cutoff. That is where we're either going to reject or fail to reject the null. So that's my critical value for z. And I'll write down my decision rule here just so that you'll have it, because I want you to be prepared for any type of wording of these problems. So for the decision rule, I will reject the null hypothesis if I observe a value. That will be my test, right? Observed z is greater than 1.65. That's my test with the critical value method. And my p-value test would be p-value less than alpha. Now what's alpha? What was 0.05? So I've set up my decision rules. I'm going to do my critical value test. I'm going to do my p-value test. I'm going to do them both and make sure that they agree with each other. So then I have to come up with what is called the observed value for z. Observed value for z. This is the test statistic. Note, the test statistic uses the sample, doesn't it? So I go back to my sample. What was my sample? My sample mean here was, can't see it here, my sample mean was 167. And I'm going to calculate it using the formula that I know to use. I'm going to say that sample mean, 167, minus the population mean, well, that's the 158, isn't it? divided by, and I had to calculate that standard deviation. Remember, the standard deviation I calculated was a 4. Now this is going to seem, that's very much what we've been doing with confidence intervals, so that should be pretty familiar. And I do this math, and I come up with a z-value of 2.25. Okay, now I want to go into my, I'm going to find another color pen here. I'm going to go into my graph here, and I'm going to say, where does 2.25 fall in relation to 1.65? Well, it's over here somewhere. Now, of course, it's probably not correct in the way I've drawn it, but that's okay. 2.25, is it in the rejection region? Yeah, it is. It was higher than my critical value of 1.65. So it looks like I'm going to, by the critical value test, I'm going to reject the null. Now they asked for one more thing. What's the p-value? Now the p-value is always the area in the tail past the test statistic. In other words, this is my p-value here. How big is it from 2.25 all the way to the end? Well, once again, we look it up on the negative side of our z-table, and we go to a z of negative 2.25, and we come up with 0.0122. There it is. So I'll write it here, 0.0122. So p-value, is p-value less than alpha? Well, p-value is 0.0122. Is that less than alpha? And as you can see, when you've drawn a curve like this, it has to be, doesn't it? It has to be less than. Alpha is 0.05 and the p-value is 0.0122. Does it pass the p-value test? Yes, it does. They both agree with each other. And we reject because of the way the test falls. P-value is less than alpha. So we reject the null hypothesis. So I'm going to write that down just so you'll have it for future, and you can use this when you're studying and when you're working your homework problems. What's the comparison with the test statistic? Well, observed z, I'm going to see, these are rewritten here with the numbers in them. Observed z is 2.25. And that is greater than 1.65. And I write it down and I say, yeah, it is. And p-value, 0.0122, this is the second test I'm comparing, has to be less than 0.05. Is it? Yeah, it is. So what do we do? What decision do we make? Well, this tells us we reject the null hypothesis. Now I've got another scenario here on page 7, and I would love it if you would try this on your own, see how far you can get, see the pieces that you can fill in. I've given it to you just exactly like I did page 6, and I want you to see what you can do with this one. I'm going to tell you right up front that this is not a left-tailed test. I'm sorry, this is not a right-tailed test. This is going to be a left-tailed test, okay? See how far you can get and then come back and listen to the explanation. Now, I know you've read this at least once, so I'm going to go through it and find this information as we go through. It says AT&T claims that subscribers to their Internet 1000 fiber optic internet service experience download speeds of at least 500 megabytes per second on average. However, many subscribers have complained their average download speed is actually much lower. So there was a random sample of 75. Now, as I find this, I'm going to write it down, of the Internet 1000 subscribers, and found that the average download speed, now this is the average of the sample, right, was 492. This is my sample average, or my sample mean. Assume the download speeds of all such subscribers is normally distributed. Okay, that's good. And all says population, standard deviation of 25. That is the population standard deviation, which they have given to me. And then they say use a significance level of 1%. Alpha, therefore, is 0.01. And ask the question, do the sample data provide enough evidence to substantiate the claim that the average download speed of their Internet 1000 plan is less than 500? Okay, so 500 is the old claim. That has to be what we are comparing it against. We'll call that the old population mean. Let's set up the alternative hypothesis. What is the claim? The claim is that the mean is actually not 500, it's less than 500. So the null hypothesis is that the mean is either greater than or equal to 500. The company just claims at least 500, so that would be greater than or equal to, right? Once again, this is like a consumer agency checking to see if the company is lying. Let's go ahead and get this calculation for standard deviation out of the way, and we'll take the 25, divide it by the square root of the sample size, 75, and we come up with 2.8868. And ask yourself which distribution. Am I using the z-table or the t-table? Well, yes, I know the population standard deviation, so I'm going to use the z-table. Now, I'm going to set up my rejection regions. I'm going to put this on a curve because this is the easiest way to make sure that I'm not making mistakes. And I'm going to draw and label alpha, or alpha divided by 2. Now, this time I have a one-tailed test, so I don't have to divide alpha by 2. Here's my one-tailed test. It's going to be over here on the left. This is my rejection region. And how big is it? 0.01. This is using the z-table, so I'm going to put that down. And I'm also going to put my population mean right here in the center of it, okay? So that I kind of know what I'm doing. You could put X bar down there so that you know you're not dealing with proportion data. All right, the next thing I'm going to do is say, what is the value for critical Z? I have to find this one, the critical Z. I have to go to my table and look up on the negative side. I would always use the negative side of Z this time. I'm going to look up 0.01, okay? Now the area I want to find is 0.01. As close as I'm going to get to it is right here, 0.0099. So that's going to be a 2.33, okay? This table is going to have as a 2.33. It happens to be negative 2.33, not because I looked it up on the negative side, but because it falls on the left side of that curve, okay? So negative 2.33 is my cutoff. So let's write our decision rule down here. We're going to reject the null hypothesis if, and this is the critical value method, okay, over here is our critical value method, if the observed value for my test statistic Z is what? Well, it would have to be less than a negative 2.33. That's how I put this picture into words, okay? Or, and this one's easy because it's always the same thing, p-value is less than alpha. What's alpha? 0.01. It's always p-value less than alpha. Doesn't matter what type of test it is. It doesn't matter if it's one-tailed, two-tailed, or right or left. It's always p-value less than alpha. That's the p-value approach, and that's really the reason it's used the most in real life. Okay, so let's look at the observed test statistic. This is the observed value for Z, isn't it? So where do we find it? Well, we have to calculate it, and we have to use the sample that we took. And we took a sample of 75, and we got a sample mean of 492, didn't we? So we'll subtract that Sitter old comparison mean, and we'll divide by the standard deviation that we calculated. And we come up with where our test statistic's going to fall. Now, our test statistic fell at a negative 2.77. I'm going to kind of draw that with a different color. I hope you can see it. 2.77. Which side of my critical value here did it fall? Well, 2.77, negative 2.77 is in the rejection region, isn't it? Because it's smaller than 2.33. And that would be how I show it. And then I'm going to, of course, find the p-value. This will be the p-value for that by going to my Z-chart and looking up 2.77. The 2.7 over here, 7.0028 is what it is. I'm going to put it here, and I'll write it down. P-value is equal to 0.0028. So now I'm going to make a decision, and I'm going to write my decisions from my decision rule. I'm doing this just so that you can make sure you understand this, okay? The first decision rule says observed value is observed value Z, observed Z less than negative 2.33. Well, what was observed Z? It's right here. Is negative 2.77 less than a negative 2.33? Yeah, it is. Now, the picture you've drawn shows you that, doesn't it? It shows you that it fell into the rejection region, but you're double checking yourself here. And the next question is p-value less than alpha? Well, p-value was 0.0028. Is that less than 0.01? Well, yeah, it is. So what do? Well, our decision is easy then, and both of our tests agree with it. We reject the null hypothesis. Okay, hopefully you were able to do really well with that one on page 7. And on page 8, you're going to be able to set up even more of this before you come back and listen to the explanation. I do want to tell you this about it before you get started. This particular test is going to be a two-tailed test. Now, since it is a two-tailed test, you're going to have to divide alpha by 2 and put a rejection in each tail. See how much of it you can fill in. So how many of these blanks can you fill in on your own, and then come back and listen to the explanation. So this exercise says, suppose the athletic director would like to know if the athletes at IRSC academically perform similarly to all other IRSC students. The mean GPA of all IRSC students, that's the mean GPA of all, isn't it, is 3.15. That kind of looks like what we're going to compare it against. I'm going to put it right here. I have to make sure that I've got it right. And like I said, you should read through it at least one time before you start writing down information, then go back and read it again. There's a standard deviation of all. That's population, isn't it? A 0.2, 0.20 or 0.2. Okay, so we took a random sample of 50 athletes, and that random sample gave us a mean GPA of 3.2. That's my sample mean, isn't it? Now, it's asking, does the sample data indicate that IRSC athletes perform, now what's the question? Perform differently. They could either be better or worse. They could be higher or lower. Differently means two-tailed test, doesn't it? And we're going to use the p-value and the critical value methods, and we're going to check at a 2% level. Now, two-tailed test. I already know it's a two-tailed test because it said perform differently. Let's go down here and set it up. Is the mean, and the question is it not equal to that of all IRSC students, or the null hypothesis would be the mean is equal to what all IRSC students are, okay? How do I do this? If I have not equal in the alternative hypothesis, and I already gave you this hint, you have to say alpha divided by 2. And let's go down here and go ahead and set up our curve while we're thinking about it, because we know at this point that we're going to have a rejection region in each tail, just like a confidence interval, right? Now, what distribution are we using? Well, we do know the population standard deviation, so we will use the z-table. And I'll go ahead and put that there. And then I'm going to put the old mean to what I'm comparing against in the center. Okay, that's where I'm going to kind of say, is it far enough away? Is it far enough higher or lower than that old academic average GPA to say that they perform differently? It has to be a significant difference before I can claim it's true, okay? So I'm going to set my critical region up, and like I said, with this one we chose alpha divided by 2, and I'm going to say my critical z, therefore I'm going to have 2 critical z's, right? This time I'm going to use both the high and the low. I'm going to go back and find just one area, 0.01, and I've done this one before. I'll do it one more time for you though. 0.01 is right here, isn't it? That's as close as I can get. You have to be really careful with all these decimals and everything. 0.01 is really close to 0.0099, isn't it? So it's a negative 2.33. That would be one of my test critical levels or critical index, and the other one is going to be a positive 3.33. Because it's a two-tailed test, if it goes either higher or lower, then I'm going to reject. Okay, so I'm going to write that down here, okay? I'm going to say I'm going to reject the null hypothesis if, and I've got 2 different ifs this time, if observed value for z is either less than negative 2.33, and then I'm going to say or observed value for z is greater than a positive 2.33, because I have 2 rejection regions. Or here's the p-value test. Same old, right? P-value is less than alpha. Now, P-value not less than alpha divided by 2. P-value still less than alpha, okay? So it's all of the rejection together. And that should set you up to think you're going to have to do something special to this P-value when you find it, okay? So keep that in mind with a two-tailed test, and I'll show you in a minute. All right, so let's find the test statistic. Let's find the observed value for Z. Where did it fall? Did it fall into one of our rejection regions? Well, we took our sample, and we came up with a sample mean of 3.2. And we're going to subtract the population mean, what we're comparing it against, 3.15, and we're going to divide by, oops, we forgot to calculate that standard deviation. We can't use 0.2. We have to adjust it and use 0.2 divided by the square root of 50. Okay, so I got 0.0283. That's what I'm going to use. 0.0283. And I come up with an observed value, a test statistic of 1.77. That's pretty clear. Now, where does 1.77 fall? Well, it's positive, isn't it? So when I found that my test statistic was positive, I really don't need this negative side at all, do I? I'm only going to look at this one, okay? So here it is. 1.77 did not fall into the rejection region, did it? Let's take a look at what that p-value is. So I'm going to go to my z-table. I'm going to look up p-value for 1.77. Now, always, I'm going to look up just the tail. So I'm going to look it up on the opposite side, all right? I'll look it up on the negative side. 1.7, and I go all the way over to the 7 column, and I come up with 0.0384. So this p-value is equal to 0.0384. But I want you to hold on just a minute, because we split alpha. See, we have a rejection region over here that's worth p-value of 0.0384. We also have one over here. We have to multiply that number times 2, okay? So every time you have a two-tailed test, when you find the p-value, you then have to multiply it times 2. Now, that's why I said pay attention, okay? P-value is compared to all of alpha, not half of alpha. So when I find my p-value up here, I'll have to multiply it times 2. So this p-value, this 0.0384 times 2 is going to equal 0.0768. Okay, here's my questions, and I'll use my decision rules to make my decisions. First, I'm going to check and see, is the observed value of Z less than, well, I don't need the negative one. I can sort of scratch that one out. I'm going to check it with this one. Is observed Z, which was 1.77, it was positive, so I'll only look at the positive side of my test. Is it greater than 2.33? Well, no, it's not. And then I'm going to say, is the p-value, the one that I had to multiply times 2, is that less than 0.02 alpha? Nope, it is not. So in both cases, my test failed, and what that means is I will fail to reject the null hypothesis, okay? Now let's take a look on page 9 at a different type of problem that you're sort of familiar with because of confidence intervals, but this is a test about the mean or the population mean when the population standard deviation is not known. When it's not known what the population standard deviation is. Now, when we've done our other hypothesis test, just in this chapter, we had a known population standard deviation. In real life, this is hardly ever the case. Much more common is that the population standard deviation is unknown, and we have to take the standard deviation of the sample and use that as an estimator. Now, we call the standard deviation of the sample S, just like we did with confidence intervals. And in the case with confidence intervals, we use the t-table, the student's t-distribution. We're going to do that again when we're calculating or we're working hypothesis tests, conducting hypothesis test, okay? So once again, I'm just going to put these formulas down for you. How do you calculate the test value, the observed value of t? It's going to be the sample mean minus the population mean, and we will divide by a standard deviation that we adjust by taking the sample standard deviation and dividing by the square root of the sample size, just like we did for confidence intervals. Now, what if the sample size, you know our limitations with our t-table, what if the sample size is too big? Well, and then you use that last row, the infinity row in the t-table, or you could use the z-table as an approximation to the t-distribution. So let's take a look at this first example with the standard deviation of the population not known on page 10. Let's take a look at this one together. It says, according to Toyota, its 2020 Camry achieves 41 miles per gallon of gasoline. That seems important. I'm going to kind of think it is. On the highway. There's a consumer advocacy agency. They're going to be looking to see if the Toyota people are lying, aren't they? And they've received numerous reports from Camry owners that the fuel economy is actually much lower. And in response, they have randomly selected 125 Camrys. There's my N, isn't it? I'm still not sure this is my population mean that I'm comparing it with, but I'm pretty sure. And they gather information about highway fuel economy, and the average highway miles per gallon of the sample was 40.06. That's my sample mean. And then it says with. Now this is of the sample with a standard deviation of 2.1. That is a sample standard deviation. You've really got to read this carefully because they don't always give you cute little hints like I have and tell you which one you're dealing with. So I've got 2.1 miles per gallon is my standard deviation of that sample that I took. And I know I'm going to be comparing against what the company claims, so I'll say that's my old population mean. And it says, do the sample data provide sufficient evidence to conclude that Toyota's claim about fuel economy is false? Now, what did they claim? They claimed that the fuel economy was at least 41, didn't they? We want to know if that's a lie. We want to know if fuel economy is less than 41. And that's the first thing that helps you. Make sure you set up that hypothesis right. It's easy to get wrong, okay? So look at what you're asking. Is the claim false, okay? To be false, the fuel economy would have to be less than what the company claimed, okay? So what's the alternative hypothesis? Well, if it's 41 or greater than, then the company's not lying. That's the null, isn't it? Sorry, that's null. This is the first one we said is the alternative. Now they want to do a critical value, a p-value approach. You want to use a 1% significance level. That's alpha is at 0.01. It's a one-tailed test. So we can go ahead and sort of draw this out here and say, okay, my rejection region is going to be over here in this tail, and it's 0.01. And I have to decide what distribution I'm using. Now, because I know only the sample standard deviation, I have to use the t-table, okay? I'll be doing a critical t. Down here, I'm going to put t so I don't lose track of that. And of course, 0 is always in the center. But what's the old mean that I'm comparing it against? 41. I'm still looking at population and sample means, right? So I'll put that down too so I know the data is what the data is. Now, let's see how big this area is. I need a critical value for t. First, I'm going to come back up here before I forget again and adjust that standard deviation. I take the sample standard deviation and I divide it by the square root of the sample size, and I come up with 0.1878. There, that's what I'll use in my calculations. And over here, I'm going to say, what is this unknown t? What's my critical value for t? Well, I've got to go to the t-table and look it up, and I'm going to use that t-table with an alpha, an area of 0.01, right? Now, with the t-table, the first thing I have to know, of course, is degrees of freedom. So how big was my sample size again? Well, it was a sample of 125. So it's definitely bigger than 124 would be my degrees of freedom, right? So I'm going to come down here to the last row, the infinity row, and I'll use that. And I'm going to look at the area, because this is a one-tailed test. I'm always going to use this one-tailed test column, actually. And I'm going to come down here underneath it and go all the way to the bottom. And I come up with my t-score, 2.3267. So let's write down the decision rule, just like we did. We're going to reject the null if the observed value for, and this time it's not z, it's t, is less than, this is a negative, by the way, a negative 2.3267. Now, how do I know it's negative? It's because it's over here on the left-hand side of the curve, okay? So, or Once again, same thing for p-value less than alpha. What was alpha? 0.01. Okay, so that's my rejection rules are all set up. And now all I have to do is find out where does my test statistic fall in all of this. First, I'm going to go over here and calculate the observed value for t. That's the test statistic. I take the sample mean, just like I've been doing, okay, 40.06, 40.6, sorry, and subtract the population mean, 41, and then divide by that standard deviation I calculated, 0.1878, and I come up with an observed value, and I only went to 2 decimal places because I saw that it was going to fall where it was going to fall, and it gave me an observed value of negative 2.13. Now, when I draw it on my curve, negative 2.13 does not get into the rejection region. It's over here somewhere, isn't it? Negative 2.13, however many decimals it is, okay? And then I will look up that p-value for that in just a minute, because this would be p-value again. And so p-value for negative 2.13, I have to go over here to my t-table again. Now this is where your t-table gets a little bit confusing, so pay close attention. You're not going to find this exactly. We can only use the degrees of freedom row that we have with the sample size, and that row for us, for this problem, is infinity. You can't go searching all over this table for the closest to value to the closest t-score to 2.13. You simply have to use this one row and say, where does it fall? Well, 2.13, I'm only going to look up the positive version of it, is going to fall between these two numbers, isn't it? Between 2.3267 and 1.9602. So I'm going to chase this column. I'm going to say it's right between these two, all the way up to the top. And this is the size of my test that I have to, and this is the size of my tail. This is going to be my p-value. It's going to be between these two numbers. Okay, I just want to make a correction real quick. Stop just a second. Let me fix something in this problem that I hopefully have already fixed on your pages. But just for our narration, let's go back and say it needed to be the sample mean, or the sample that mean was taken was really 1.69 ounces instead of 1.68. Okay, can you fix that for me? And then if you do that, and I should be right on my video now, I want to match your pages. 1.69 minus 1.62 gives me that t-score of 3.196, which is what I was looking at putting down for you. Okay, so 3.196, I draw it in my rejection. Definitely doesn't need the negative side, but I draw it in over here and put it on my positive side. It looks like it falls into the rejection region. And now let's do the hard part with the t-table, which is let's see if we can find p-value, okay? So we have to say 3.196, degrees of freedom 29, right? And we're still looking for only one side of this test, because I'm trying to be consistent with you and only use that bottom header up here only looking for one-tailed test, even if it's a two-tailed, because we've already split it into two pieces, all right? So I'm going to go 3.196 on degrees of freedom 29. Don't forget that part. Falls between, see, I don't think I have it on your screen. Hang on. Falls between these two numbers, doesn't it? So I'm between these two columns, and I'm going to go all the way up to the top and see what that means for my area. Well, it's between 0.0005 and 0.005. That's what it is. So I'm going to write that down. So p-value is a range, right, between 0.0005 and 0.005. However, I have to multiply it times 2. So when I multiply it times 2, it comes out to be 0.001 and 0.01. I think I got that right for you. That's your p-value between 0.001 and 0.01, right? So let's say if p-value is in that range, 0.001 to 0.01, is that indeed less than our alpha, which is all of alpha? That's why we multiplied by 2, right? So all of alpha, which is 0.02, and it actually is. So it matches our test for the test statistics. So finally we get to make our decision. Let's go over here and write our test down. I said observed value of t came out to be 3.196. It had to be greater than 2.462, and it is. And the p-value of somewhere in this range had to be less than 0.02, and it is. So what do? Well, as you can see up in your illustration, and our decisions should match that, you reject the null hypothesis. Now I've got one more of these for you on page 13, and by now you should be able to go through and do this all by yourself. I want to give you a chance, though, looking at the p-values and using the t-table. So try this one, and then come back and see how much of it you got right when you listen to the explanation. This problem says the management at Massachusetts Savings Bank is always concerned about the quality of service it gives its customers. Now, the old computer system, a teller at the bank could serve 22 customers per hour. Now, I'm thinking since that's the old computer system, that's probably what our mean's going to be, but let's keep going. The management noticed that this service rate, the waiting time was too long, so they installed a new computer system, expecting it would increase the service rate and make customers happier. It would reduce the waiting time. They want to check and see if the new computer system is more efficient than the old one. So the management took a random sample, I know that's my sample size, right, of 70 hours and found that during these hours, the mean number, so this is the mean of the sample, was 27 per hour, and it had a standard deviation of the sample, didn't it? 2.5. So I'm going to go back and say this 22 per hour is what we're going to compare it against, because I'm pretty sure now. Now, testing at the 1% significance level, there's my alpha. Would you conclude the new computer system is more efficient than the old? Now, that's kind of worded strangely. What would it have to be for the newest system to be more efficient than the old? We would need to be serving more customers per hour, right? We need to be serving more than the 22. So I'm going to say that's my hypothesis, is that the new computer system is better, therefore we're serving more than the old. Now, you could have gone the other way. On this one, sometimes your hypothesis could be worded differently depending on you as a researcher, but your problem should be fairly well straightforward here and easy to identify. Now let's go ahead and do this. We're going to use the t-table because we only have a sample standard deviation. I'm going to go ahead and do my calculation for standard deviation by dividing 2.5 by the square root of n. And when I do that, I got 2.2988. And then I'm going to look at my curve and put this all on the curve. I say I need a rejection region. It needs to be over here in the right tail. It's a right tail test. There's my rejection region. And how big is it? Well, it's all of alpha. This is the t-test. And the mean I'm looking at in the center is 22, isn't it? And over here, I don't know what that critical cutoff is. That's my critical value, and I'll have to figure out what that is. So it'll be a critical t, and I'm going to look it up. Okay, now what am I dealing with? Well, I'm dealing with the t-table, so I need to know degrees of freedom. In fact, for this whole problem, I'll never look on the t-table beyond that one row, which will be degrees of freedom 69. So I'm looking for 69, and I'm looking for an area of 0.01. So here is my t-table. The row is 69, degrees of freedom 69, and then I want to go all the way, let's see, I'm going to go all the way to the top and see where is the row of the column. Is this 0.01, and I'm going to have to keep pushing my page up. Here you go. And this is the column I'm interested in. I get 2.3816 is the t-score. That's the critical value. It's 2.3816. I'll put it down, 3816. That's going to be my cutoff. So everything's pretty clear. I will reject the null hypothesis if, when I do my test, I observe a value of t that is greater than 2.3816, or p-value is less than alpha, which is 0.01. So let's figure out, what is this observed value for t? I did the test. I took the sample. I came up with 27. I'm going to subtract the old mean of 22 and divide by the standard deviation I had to calculate, 0.2988. And then I'm going to get a test statistic of 16.734. Well, I've never seen a t-score that big. Where does that fall? Well, way over here. Is it rejected? Yeah, I'm pretty sure it is. What is the p-value going to be for this one? Well, let's see if we can figure that out, okay? Let's go into degrees of freedom 69 one more time. Degrees of freedom 69. And let's see if we can find the number 16. Well, it's not here, is it? Where would it be? Way over here, past this first column. So let's go up to the top and say it's going to be over to this side of 0.0005. So it'll be smaller than, because they get bigger as they go to the right, don't they? So it's going to be smaller than 0.005. 0005. So this is going to be less than 0.0005. That's the only thing I can say about that p-value, isn't it? What is p-value? Less than 0.0005. Very small p-value. So now let's do the comparisons here. I'm going to say observed value for t, that was it was 16.734, had to be greater than 2.3816, and yep, it is. P-value, which came out to be, I'll put it in brackets so you can see I'm saying it was a range, less than 0.0005, and that had to be less than our alpha of 0.01. Yeah, it is. So our decision here is pretty easy. If you couldn't have told and you could tell, it's all agreeing. We reject the null hypothesis just like it showed us on our graph. Now let's do our third type of problem. Just like we did in confidence intervals, we now are going to be dealing with proportion data. So up until now, we've been talking about population mean. We've been doing hypothesis tests to determine if a population mean is as it claimed to be, but we're going to focus now on a different parameter. We're going to talk about a population proportion problem. So fortunately, the test methods and the steps don't change at all. We still apply the critical value approach or the p-value approach. The only difference now is, just like confidence intervals, we're working with p and p-hat. So we'll calculate the test statistic using the familiar formula. It should be familiar to you now. For z, we're going to say p-hat minus p divided by that standard deviation that we calculate. How do we calculate the standard deviation for these? We say the square root of p times q divided by n. Now notice, we're saying p times q divided by n, not p-hat times q-hat, and that's important because in these problems you will have both p and p-hat available to you. Make sure you use the right one to calculate the standard deviation. So let's go through and do a couple of examples with this one, and we're dealing with population proportion data this time, and so I've sort of split it out for you. And your first example, okay, is going to be not on page 14, it's going to be over here on page 15, okay? So this problem says a family is referred to as food insecure when the family is uncertain of having or unable to acquire enough food to meet the needs of all members because they have insufficient money or other resources. In 2018, the U.S. Department of Agriculture found that 11.1%, that's what tells me this is a proportion problem, okay, of U.S. households were food insecure at some time. A nonprofit believes the proportion of food insecure families has actually increased. They think it's increased. A random sample found that 32 out of 200, all of this is pointing to proportion data, right? 32 out of 200 families reporting being food insecure. Now, does the sample data support the nonprofit's belief that the proportion of food insecure families has increased? They want to say it has increased since 2018. Since, try to change that word if it's not changed since. Use the critical value and p-value methods and a significance level of 5%. So we're going to say alpha 0.05. We have got a sample taken. What was our sample? A random sample said 32 out of 200. So the sample was 200. When they took the random sample, they found 32 out of 200 were insecure. That's going to be my proportion, right? My sample proportion. I would say 32 divided by 200, and I'm going to come up with the number 0.16. Now, what does the Department of Agriculture says? Well, 11.1% or 0.111%. So that's the population proportion. The one I'm going to compare it against is 0.111. The Q, therefore the Q value associated is going to be 1 minus 0.111, and I would say that's 0.889. Now I need these two to calculate the standard deviation. Note the standard deviation is calculated using P and Q, not P hat and Q hat, okay? So you're going to have both P hat and Q hat in these problems. So you're going to have to use the right one to calculate standard deviation. So what do I do for standard deviation? Well, I say 0.111 times 0.889. I divide it by 200, and all that's under the radical. And I come up with 0.022212, and it's a good idea for proportions to use 6 decimal places when you're dealing with standard deviation. So we are going to set up now our alternative hypothesis. What does it say? They want to know, the nonprofit thinks that this proportion has increased. In other words, they think the population proportion is actually bigger than the old comparison one, the one that is always going to be in the p-value, the population proportion, the one that the Department of Agriculture claims, okay? So the opposite of that is that it is not greater than, it's either going to be equal to or less than. We've got our hypothesis set. It's a proportion problem, so we always use the z-table for proportion problems. So we're back to the z-table again, and we're going to set up our hypothesis just like before. We're using z. Let's put the population proportion that we're comparing it with here, and let's say we want to know if it is greater than it used to be. Here's my rejection region, and it's going to be all of alpha since it's a one-tailed test, and I need to figure out what that critical z is. So for critical z, I'm looking for 0.05, and we've done this one before. Remember, it's on the positive side, but we're still only going to use the negative side of this table to look these areas up, and I come up with 1.65 is what I'm going to use. I'm going to use a positive because it's on the positive side. So I'll say critical z is 1.65. Now you're going to have to make sure, you're looking them up on the negative side because you're interested in the tail. Even if the tail I'm looking at is on the right, I'm still going to look it up on the left so that I don't have to do the subtracting from one thing. Okay, so I've got it all set. I'm going to reject the null hypothesis if I observe a value for z that's greater than 1.65, or if the p-value is less than alpha. What was alpha? 0.05. Same thing. I mean, basically, this is not much different, is it? All right, so we're going to check our observed value for z. We'll do the calculation. We'll take the p hat this time. The sample was 0.16. Subtract the comparison, which I always have put in the middle so I could check myself, and divide by that standard deviation I had to calculate. and I come up with a z of 2.21. That's my rejection, that's my test statistic. Where does it fall? Well, it's definitely over here, isn't it? 2.21, and then I can figure out what that p-value is. I go back to my z-table and I look for a z, and I'm going to look on the negative still, 2.21, and it is, what is it? It's 0.0136. So this area is p-value is equal to 0.0136. Okay, so p-value is equal to 0.0136. Let's write our comparisons down. The first one was if observed z, which happened to be 2.21, had to be greater than 1.65. And yes, it is. We can see that on our picture here. And the p-value, which came out to be 0.0136, had to be less than alpha. And it definitely is. So we will get to reject the null hypothesis. In other words, has the sample data, does it support the nonprofit's belief that the number of food insecure families has increased? Well, yes, it does, because we rejected the null, which says that the food insecure family proportion has not increased. Page 16 is another proportion problem. And just to kind of give you some hints as you go, I want you to try this on your own. I really would love it if you could get as far through this page as you can before you listen to the explanation. And this one is also going to be, just to help you out, a right-tailed test. So our problem says that when working properly, a machine that is used to make chips for calculators does not produce more than 4% defective chips. I have a feeling that's going to be my population proportion there, but let's keep going. When the machine produces more than that, it needs an adjustment. So to check if it's working properly, quality control takes a sample of chips, inspects them, sees if they're good or bad. One such random sample of 200 chips, there's my sample size, take it recently, it gave out of that 200, it contained 12 defective chips. Okay, that's the sample, so I know I've got my sample proportion. What was it? Whoops, it was 12 out of 200. 12 out of 200, when I do that, is 0.06. That's a 12. 12 divided by 200, okay? So that's my sample proportion. And I want to find the p-value to test the hypothesis, whether or not the machine needs an adjustment, and make the conclusion. What would the conclusion be if the significance level is 2.5%? Now, if I find that I have less than 4% defective chips, am I going to have to make an adjustment? No. So I'm going to be checking to see if the proportion of chips is greater than my cutoff, which is 4%. If I do my test and it's less than or equal to 4%, I don't have to adjust the machine. So what comparison? I'm doing a comparison against this standard, 0.04. That's going to be the population proportion. I would subtract it from 1 and get Q, which is 0.96. And I'm going to be checking at the 2.5% or 0.25 alpha level. Let's go ahead and do the standard deviation calculation, taking P, multiplying times Q, and dividing by N. Everything's under the radical sign. And that came out to be 0.013856. I'm going to use the z-table because it's a proportion problem. And I'm going to go ahead and draw and label my curve, okay? Now I'm going to have the rejection following the alternative hypothesis. Rejection over here in the right. And how big is this rejection area? Well, it's all of alpha. This is a z-test. The center of it, I will say, is the proportion that I'm comparing against, and I need my critical value for z. Now, how do I find it? Well, I go to the negative side of the table because I'm, once again, looking up an area in the tail, and I go 0.025. 0.025 is right here. It's one that I should be familiar with. It's 1.96. Well, it says it's negative 1.96, but I'm on the positive side because I'm doing a right-tailed test, so that's a positive is what I'm going to compare. And if when I do the test case, if I observe a value of Z that's greater than 1.96, I reject. Or if I observe a p-value that's less than alpha, which is 0.025. Now, what is observed Z? Well, let's take our test statistic and find out. We had a test statistic of 0.06. We're going to subtract the comparison proportion of 0.04 and divide by the standard deviation. And this comes up with 1.44. So p-value, therefore, for 1.44, where is 1.44? Well, 1.44 is not as big as 1.96, is it? Right in here, maybe? Let's go check the p-value on 1.44. Once again, go to the negative side of your table, because you only want area in the tail, and that's why we're doing that. And go over to 1.44, and you get 0.0749. Okay, 0.0749. So that's going to be my p-value. Let's take our decision rule and come down here and write it out, just so we have that. If the observed Z, what did I observe for Z? 1.44. To reject it had to be greater than 1.96, but that's not. And the p-value, which is 0.0749, had to be less than alpha, which it is not. So what happens? Well, we fail to reject the null hypothesis. We don't know, the null hypothesis might still be wrong, but not by our test, okay? Our experiment did not show that. Now I want to note something here for you, because I'm going to get an email about this from somebody, and it is calculating the standard deviation. If you have a problem that does not give you a standard deviation at all, if it doesn't, like this one, then chances are you've got a proportion problem. The only other choice would be if you were given the actual data values, so you had sample data and you had to do the calculation like we did back in chapter 2. So that's clues for you of what type of problem you have. When do you have proportion problems? One thing is there's a lot of percentages, right? But the other thing is no standard deviation. I had to calculate it using P, Q, and N. Page 17 has our last example in it. It's another proportion problem. I'm going to give you the same hint that I always give you and tell you that it is a left-tailed test that you're going to be performing. And hopefully you're able to do this one all the way through before you listen to the explanation. Now this problem says Direct Mailing Company sells computers and computer parts by mail. The company claims that at least 90% of all orders are mailed within 72 hours after their receipt. Well, that looks like a proportion to me. So 90% they're saying are mailed on time within 72 hours. Quality control takes samples to check to see if it's valid. They took a recent sample of 150, and they showed out of that 150, 129 are mailed within 72 hours. In other words, 129 are on time. So is the company's claim true? Now, we're going to check and we're going to say, I'm going to check like saying, is the company's claim, I'm going to look for the company's claim to not be true, okay? You could have checked to see the other way, but that's just the decision I made. I'm going to say, is the proportion of packages made, is it less than what they're claiming, what our standard is, 0.9? And I have up here 0.9, 90% are mailed on time, right? Now, I can also say, once I know that that's the check I want to do, because I'm quality control, so I always check to see if, we're not up to what we are supposed to be. And really, it could go either way with these. You probably will have more hints than that on your word problems. The opposite of that would be the proportion of packages mailed on time is equal to 90% or greater. Okay, so that would be fine. But this is my quality control check. Are we not living up to our standard, what we need to do? Now, the sample says, a sample of 150, 129 were mailed on time, so I'm going to go 129 divided by 150 to get that proportion, and I come up with 0.86. Now, I got P of 0.9, so Q is going to be 1 minus 0.9, or 0.1. I want to check at a 2.5 significance level. And let's calculate the standard deviation. I'm going to say 0.9 p times q divided by n. There were 150, right? And when I do that, I get 0.024495. I'm going to use the z distribution since this is a proportion problem, right? And let's go ahead and draw the curve based on what I told you before. It's a single-tailed test, right? It's going to be over here. Look, my alternative hypothesis points me toward the left tail. That's my rejection region. How big is it? All of alpha. And it's a z-test. And what is the center proportion I'm going to be comparing against? 0.9. Okay, I'm pretty much set up. I just need the critical value for z. I need to know what that cutoff is. I've got 0.025, which I'm pretty familiar with by now. I almost know what that one is without going to the table. It's negative 1.96. And do I need the negative or positive? Well, I actually need the negative because I'm on the left-hand side of the table. So I will reject if the observed value for z is less than a negative 1.96, or if p-value is less than our alpha 0.025. So let's do the test statistic. Our observed value for z is going to be the sample that we took, 0.86, minus the center that we're comparing against, 0.9, divided by the standard deviation we calculated. And I get a negative 1.63. Where does that fall? Negative 1.63 didn't get into the rejection region, did it? But we'll go ahead and do the p-value test anyway. Let's go to negative 1.63. Here it is, and we find the area is 0.0516. 0.0516. That's the p-value. And let's just go ahead and write our decision rules with the information we found. Observed value of z came out to be negative 1.63. Is it less than a negative 1.96? Well, no, it's not. And the p-value, which came out to be 0.0516, had to be less than our alpha value of 0.025, and it's not. So what happens? We fail to reject our null hypothesis. Now, we're quality control. We're checking to see if our machines are okay, and we failed to prove that our machines were, our customer, what was it, our orders were being sent on time, and we failed to prove that they weren't, that enough of our orders were not being sent within 72 hours. So actually, this is a pretty good thing. We're pretty happy to reject this null hypothesis. Now I've added one final page for you if some of you want to play around with your calculators, and I'm not going to go to too much of an explanation with this because it works so differently for all of your calculators, but you can find in your calculator how to do a z-test, how to do a t-test, and how to do and it's called a 1 minus proportion z-test, okay? A 1 minus proportion z-test. You might want to try playing around with that if you desire, and see what your calculator does with those. I'm not going to go too much into it because I think that the method I've given you for calculating and using your t-tables is probably the best for you to learn how to do this information. This concludes what we are going to do in Chapter 9, and you should be able to do the work, your homework and quiz, and start getting ready for your last test, which is our final exam, which is Test 4. It only covers, however, Chapters 8 and 9.